Okay, good day to each and every one of you. We have here a problem concerning about beams, and our goal for this problem is to solve the internal forces that is acting inside our beam. Okay, so first we have here at point A supported by a pin, and at point D we have here a roller as a support, and the dimensions from point A to point B is about 2 meters. From point B to point C is about 3 meters. And from point C to point D, it's about 2 meters. And then we have here a force acting downward, somewhere in between section A to B, equivalent to 14 kilonewtons. And we have here 28 kilonewtons, exerting a downward force from section B to C, equivalent to 28 kilonewtons. And a step in solving beams, of course, because it's supporting vertical forces, oscillating force, we must first solve for the support reactions, because according to the laws of statics in your mechanics 1, we need to somewhat get first the forces that is being supported by the pin and the roller. And in order for us to solve the internal forces of this beam, is that we need to do the method of sections. Since we have three segments, because we have A, B to C, and then C to D, we must do a method of sections three times, which is for this one, that is section 1, then for this one, that is section 2, and last but not least, for CD, that is section 3. Okay, and upon doing that, we can somewhat solve for the shear stresses that is on each segment, and of course the bending moment formulas. So upon doing that, let's try to solve first for the reactions. So again, for the reactions, just need to do the summation of moments. It depends on you where you are convenient or where you are comfortable in starting. But for me, I'm going to try in using the summation of moments. I can go with A or I can go with D. So for this case, I'm going to start at D so that I can solve for R sub A. Okay, so let's do that. Summation of moments here at point A. Just going to remove this. Okay, clockwise is positive. Summation of moments at point A is equals to 0. So the forces that is acting here at A is we have 14 kilonewtons rotating rotating clockwise, because we assume that any force that is rotating clockwise is positive. So we have here 14 kilonewtons. The perpendicular arm is 2 meters, so that should be 14 kilonewton multiplied by 2 meters. Then we have 28 kilonewtons also rotating clockwise, so that should be positive. 28 kilonewtons multiplied by the perpendicular distance, equivalent to 2 plus 3, that's 5. So 5 meters. And last but not the least, the reaction at D. So the perpendicular distance is 2 plus 3 plus 2, so that should be 7. Then it is rotating counterclockwise, so that is negative. So R sub D multiplied by 7 meters. And after that, we need to somewhat isolate R sub D so that we can solve for its equivalent value. So R sub D multiplied by the moment arm, 7 meters, is equals to this, everything. So we have 14 kilonewton multiplied by 2 meters plus 28 kilonewtons multiplied by 5 meters. Then dividing both sides by 7 meters. Okay, 7 meters. So cancel, and the equivalent value for R sub D is equals to, so upon solving, that should be 24 kilonewtons. This should be 24 kilonewtons acting upward, because our initial assumption for this structure is that at support D, it is acting upward because it is resisting these forces, 14 kilonewtons and 28 kilonewtons. So that's why it's acting upward. And then we have a positive answer, means to say that our initial assumption for the reaction support here at R sub D is correct. So it's positive because it's acting upward. And the next one is to solve for R sub A. Then we can just simply use the summation of forces along the vertical axis. Going up is positive. So going up, summation of forces along the y is equals to 0. Going up is positive. We have here 14 kilonewton going downward. So let's just retain the unit so that we can have excess space. So that should be negative. Okay, that's negative 14 minus 28 because it's acting downward. Then we have R sub D going upward, so it's positive. That should be 24. And last but not least, R sub A going upward, so that is positive. Then isolating R sub A by transposing everything here, going to the left and then rearranging the terms. So that should be R sub A is equals to 14 plus 28. Then this one becomes negative 24. So R sub A is basically equals to, upon solving, that should be about 18 kilonewtons. So this should be 18 kilonewtons, and then our initial assumption is that it's going up. So we have a positive answer, meaning that our initial assumption is correct. So we managed to solve the reactions. So I'm just going to write it here. R sub A is equals to 18 kilonewtons. And then R sub D is equivalent to 24 kilonewtons. 24. Okay, so we managed to solve for the reactions. And the next step that we must do is to apply the method of sections so that we can solve for the internal forces acting on the beam. So upon doing that, let's try to solve first for section AB now on the left side. So we're going to consider the left side of each section all the way from A to point D. Okay, we're going to use the left side. It's going to use this free space. So using the left side of this structure for section AB, okay, we're going to start here at AB. So upon doing that, section A-B, using the left side, of course, let's draw the free body diagram. Okay, this is the free body diagram, and then this is the point where we cut the section AB, as you can see here. So we have here at this point, this is A, we have a reaction R sub A equivalent to 18. Okay, this is 18 kilonewton. And from this point where we managed to cut section A-B, we have here the shear force going downward. Okay, this is, you can assign that anything. This is V sub A. And of course, we have the bending moment because the beam is supporting transverse loads. So that's the main function of the beam, of course. It's designed to resistance those forces. So this is moment sub A. Okay, so this is the representation of our section A-B. And then from here on, we need to solve for V sub A and M sub A. And since we don't know what is the exact distance of this from point A all the way to the point where we managed to cut section A-B, so let's assign this as distance x. This is distance x. Let's solve for V sub A. We can just use the summation of forces along the vertical axis. Okay, this is positive going up. Summation of forces along y is equals to 0. So that should be 18 kilonewtons. Kn. And then we have negative V sub A because it's going downward. Means to say V sub A is equals to 18 kilonewtons. So we have a positive answer, meaning to say that this shear force V sub A is going downward. And using the summation of forces of moments at this section where we managed to cut section AB. So we're going to use the summation of moments at this point. Okay, so summation of moments going counterclockwise is positive. Okay, summation of moments equals to 0. We are uh, targeting the pivot point at this section where we cut section A dash B. Okay, so is equals to, we have here positive m sub A because it is rotating counterclockwise. So m sub A, and then cancel v sub A because that is where the pivot point is located. And we have here 18 kilonewtons rotating clockwise, so that is negative 18 kilonewtons multiplied by its perpendicular distance equivalent to x. Then isolating m sub A, that should be 18x. We just need to somewhat retain the units because by the end of the day it would still be the same, kilonewton meter, because x is in meters. So again, since we managed to solve for the left side of this section A dash B, this is the shear, this is the shear force acting at this section, and we have here the bending moment acting at this section where we managed to cut section A dash B. So this is the formula for the shear force and the bending moment. And next one is we need to solve for section B dash C. Okay, that is the second target that we need to solve for this case.